Et la dernière présentation pour ce matin, c'est Hassan Chaitou qui est à Télécom Paris avec Thomas et Jean Lenôtre et Laurent Potet. Et je vais juste arrêter le partage chez nous parce que si je fais, normalement, vous pourriez probablement partager. Je vais juste faire ça. Sinon, je dois cliquer quelque chose d'autre. Tac, je vais juste arrêter ici. Stop. OK. Et je vais faire vous le présentateur. Make presenter. Unable to make the selected attendee presenter. Vous présentez de quel ordinateur? De...
You should be able to see the presentation now, no?
Yes, it works perfect. It's only not on my screen here, but yeah, it's fine. Good.
You can
Yeah, so I'm Hassan, then I hand over to you, and we're looking forward to your presentation.
Oh, wait. No, it's okay. Don't change anything.
So hello everyone. So it's my pleasure to be here today to present my updates on my PhD. I'm at my third year of my PhD, which is entitled Optimization of Security Risk for Learning on Heterogeneous Data, under supervision of Thomas Robert, Jean Lenôtre, and Laurent Potet. And so today, in this presentation, I will start with some observation from previous result, and then I will talk about the current contributions, ongoing work. I will end with conclusions and future works. And so for this PhD, it's about understanding how the activity is observed and how the quality of data used during the IDS training and how this can impact the performance of the IDS detection. And at the beginning, if we want to understand this detection performance, we need to start by identify how we can make the IDS robust against evasion attack. So previously, in previous work, we studied evasion attacks, which is kind of meta attack in which the attacker tries to boost the evasion performance of the attack based on some existing known attack. And basically, this is done through a component called attack generator. And that process a perturbation to the existing attack so that it evades the detection of the IDS. In this context, the previous study was about how the resource spent can change the performance on both sides, so on the defender and the attacker sides. And this was part of a paper published on CSR. It was about experiment that shown that if we consider different way to spend resources to train better attacks, or better attack generator on the attacker and defender sides. And we have some kind of race in terms of resources spent that affect the performance either for the evasion or for the detection. And thus it means that it's a matter of resources spent on both sides. So to master the risk associated with the evasion attack, and so yet we observe some odd observation is that for particular type of attack in the data set, there's either we have this nice scaling effect, but in other situations we notice that there's are cases that for particular type of attack or particular type of data, we never managed to correctly design an attack generator that could perturb the system that satisfy the both cases, not impairing the effect of the attack or evading the detection. So we need to understand this problem of inability to generate such evasion attack. And in this situation, related to the criteria to keep the attack relevant after perturbation, or it's related to the fact that potentially there's some kind of interplay between the attack behavior, the criteria to perturb the samples, and the content of the data. And so here we could have some hidden properties about the actual content of the dataset or of the quality of the dataset. And so this current work was accepted on a secret conference that will be published on next July. So at first, in order to understand our contribution, we need to introduce some background knowledge about the quality criteria of the dataset. And also we need to understand how the attack generators works on the criteria that we rely on to obtain the impactful and efficient evasion attack. So in this work, we focus on one particular issue with the dataset quality because this issue is very related to adversarial sample generation, and which is a contradictory dataset. So a contradictory dataset by definition is considered, so we consider a dataset as contradictory if it's contain a contradictory sample. Meaning if we observe a normal activity or attack activity for supervised learning, we do generate a samples as a vectors of values or features in the data world. And also we need to generate a label for this observation. The label tells us what is the activity about. So for instance, it's normal or attack. So the problem here, so even those two observations are not representing the same activity, we say that we have a contradictory sample if the label part are different, but the observation part is the same. So this kind of issue is already considered for standard machine learning domain, but this problem becomes less important, let's say, in the image or computer vision domain, because we have thousands of dimensions, thousands of data points for each observation. But in the domain, in the security domain, most of the data set in the network have less than 100 dimension, and with a few data points that have large integral of number, because the data types here is even binary, categorical, or continuous, so such as the protocol type, the surface type, and so on. So this problem could be more frequent to happen or encounter in the case of intrusion detection systems. So this problem of contradictory dataset is already handled for most dataset, but yet here we are working on adversarial training, so which is basically based on extending the dataset by adding new data points, and potentially we could reintroduce this issue of contradictory samples. So what's the adversarial training? Adversarial training is involves of extending a training dataset with adversarial samples before training an IDS. So it relies on an attack generator that's used by the defender to generate those adversarial samples. So those generated samples are then added to the original dataset, and the IDS is retrained on the new dataset, as we shown in the image. So we have two steps: the generation step and the retrained step. So here, the gray one is the original data set. The red one is the generated adversarial. So we add this together and retain the IDS on them. And here, there's another things to take into account when generating adversarial sample, is that we need to learn which kind of noise is more likely to evade the attack. And here we have two constraints that must be taken into account. The first one is the semantic constraint. So if you generate an attack sample, we must keep the actual attack behavior of the activity during the mutation or after the mutation. And the second one is evasion constraint, which is it's a way to maximizing the evasion capability. So here we have two questions arise. So the first one is when we generate and adding this adversarial sample, do we impair the quality of the dataset by reintroduce the problem of contradictory sample? And the second one is do we really understand those two constraints to understand what's the semantic of the features and so on. And when do we handle these two constraints? It could be a reason for the first problem of the quality of data if we don't manage correctly those constraints. So furthermore, there's a side question in this context. If the attacker handles those constraints differently from the defender, would it make the attack more efficient? And so in the literature, what we observe is that these constraints that about able to generate the perturbations that keep the attack behavior after the mutation in most cases were poorly studied. So and so in this contribution, first we start by formalizing these concepts we made this formulation offer to understand those issues that were presented in papers. Also, this formalization helped us to identify clearly the different threats related to the question we asked. And finally, we propose some mitigation and experimentation to assess the level of risk of these threats, and we test the uselessness of this mitigation. So the first thing we need to formalize is how do we respect the constraint during the generation of evasion attack, so that mutated activity actually remain an attack. So as we said before in the literature, usually this problem was not a main topic of the research study, but more recently, the community start noticing this concept, the importance of this concept. So this concept was showed first in NSL-KDD, where the author simply state and claimed the constraints of different types of attack. But in fact, there's no real discussion why their criteria to identify a valid perturbation on the observation is actually correspond to an actual attack activity. However, to our knowledge, for now, this dataset is the only dataset that in network security that have provided such level of knowledge. Well, there's some other alternatives that the researcher agreed that it's an important concept, and some propose some statistical method to learn it, but yet no actual method is proposed to validate the proposed learning methodology for this statistical approaches. So in this work, I will not talk about how to learn this concept. I will just assume that this concept exists, and what it means formally and the consequences if this concept exists, and to understand the importance of this concept. So to formalize this concept, we will call it impactful neighborhood of an attack sample, INA, which is a set of all possible mutation applied to a malicious sample that does not change its actual impact. So people studied INA, but they never understand its impact. So if you know the rules to tell which element is belong to this concept INA, then you can define the set of all samples that can be reached to be evasion attack, as we can compute them from an original data set. So the question here is this set can contain any situations that we could lead to a contradictory sample. And if this is the case, it means that some adversarial samples are contradictory samples, and then some adversarial training dataset are contradictory dataset. So we have this definition of extending contradictory samples or dataset, EC, which contain all the contradicting samples that are in the original dataset, beside all the contradicting samples that could be obtained through adversarial training. And so there's this interesting situation that can we find an attack sample that are related to the elements that are inside the INA and have contradicting with normal samples in the original data set. And so we will call this set of elements as best deviation candidate of a data set or peak. So this set is very interesting for two reasons. The first, because this sample could cause potential quality issues for the data set, for the original data set. And it's also interesting for the attacker because in an original data set, there's a sample that's labeled as normal with an observation that could be, could the attacker reach from an attack activity through a perturbation of an original attack activity. This means that it's very likely that the IDS will classify this mutated attack activity as normal. So if the attacker knows this kind of element or how to reach this set of element, this is the perfect evasion attack sample for the attacker. And so one of our contribution is to identify the major threats on robust IDS's performance using this knowledge of INA and EC. So the first threat we identify is the self-poisoning threat, which is if adversarial training is performed for an IDS using the attack generator, for which it cannot prove that a mutation does not respect INA because in this case, the defender does not consider INA. Then this training procedure is set to poison to the IDS training dataset. This could lead to add bad samples, such as normal samples labeled as an attack into that IDS training, and so on. The second one is the testing cost threat, which is the defender here know the importance of the INA concept, but he doesn't know how to explore it. So in this situation, the defender wants to stick with the concept of only adding the impactful adversarial samples. So he tests the observation of each sample manually, and this is very costly for him. The third one is related to the data set equality. So this threat, the confusion normal sample threat. So this threat is about the problem of the data set equality. So here we have INA defined, but we have the normal samples that are looks like attacks in the data set. So those samples are responsible for generating contradictory situation while generated adversarial sample. And the last one is the best deviation attack threat, which here the attacker wants to, if he wants to remain undetected, he can only apply the evasion attack from the peak set because it's mostly likely to succeed from the first try. And so we propose 3 mitigation against this threat, but here for the first 2 threats, the self-poisoning threat and the testing cost threat, actually we cannot mitigate them unless we have some knowledge of INA. Even we need to comply with INA or to approximate INA. Otherwise, it's very hard to mitigate against these 2 threats. So now let's assume that we have INA. So the first, I don't know what happened. Okay. So the first mitigation is the sample removal. So here we remove the normal confusion sample that looks like an attack and from the original data set. That's responsible to generate contradictory samples from adversarial generation. The second one is the pessimistic relabeling, which here we go further steps than the first one by using those confusing normal samples as an attack samples. And basically, these 2 mitigations are, we can apply them for the third threat, which is the confusion normal sample threat. And the third mitigation we propose is oversampling of peak here. This strategy consists in increasing the likelihood of generating the peak samples. So this mitigation can be applied against the fourth threat we have, which is the base evasion attack threat. And so moving to the experiment, the objective, we did many experiments. The objective of this experiment was to assess how the threat impact the performance of the IDS, and the second objective is assess how the mitigation are actually a fight against the threat impact. But before that, to understand the experiment's object, We use three important metrics, the recall, which usually called the detection rate in security community, the aviation increase rate, which is the increase in the undetected adversarial malicious traffic example by the IDS compared to the original malicious traffic example. And this metric is usually used from the attacker point of view. And the aviation reduction rate, which compared how well a robust IDS can resist adversarial samples compared to a less robust IDS. So here we use AIR to compare the IDS trained without adversarial training to the various IDS that takes advantage of the mitigation strategy. And this metrics take the defender point of view. And for the first experiment, we want to see what is the impact of the threat we consider it. So we know that adversarial training scale is important with the amount of resource spent. So basically, when we want to see the impact of the threat, we need to compare the impact on different level of resources. So here we use different size factors, parameter for building the adversarial training comparing to the original dataset by using the size factor of 1, 2, 5, and 10. This leading to extend the dataset of 81, 82, 83, 84, and we train the IDS on this dataset. So we have 4 new IDSs. And so the approach we use in this experiment is that we assess the performance expressed in AIR and the various adversarial training procedure for different level of resource to assess the threats and the mitigation, and also to understand how the impact scale with the resources investment level. Also, because we use GAN here as an attack generator, we repeat each experiment 50 times. So this statistical test is just to avoid the effect of the randomness in the GAN generator. So we notice here that the risk of adversarial evasion attack depends on the size of the investment resource. As here for IDS 84, which is a very costly IDS in terms of training, is the best robust IDS with AIR quality about 90%, 0.9, while the weakest IDS OD, which an IDS that trained on original data sets. So we don't apply any defense mechanism here, so has completely defeated by the attack generator. And so we notice that adversarial training works well, but at the expense of scaling factor that are 5 or 10 times the size of the original data set. So it's very costly. So just for now, for the next experiment, we will focus on 82 because it's in the middle of this, has the middle performance, so we can compare them with other IDSs. A second experiment we did is to assess the impact of the threat. So if you want to assess a threat, we should consider a data set with or without the issue by comparing here a regular adversarial training ADS 82 to that have the issue of quality data set, and with data sets that do not have here because we try to mitigate to assess the first mitigation, which is a normal confusion sample. So here the other data set, the IDS trained on 82 WN, we remove this confusion sample from the data set. So so we can see that the AIR here is very different, given that the test set is the same in both cases. So we can see that the adversarial training performance improved like from 0.4 up to 0.57. In addition, we did experiment 3, which compares the first two mitigation, the first mitigation and second mitigations. And what we observe is that without confusion normal samples, the performance of adversarial training behave better than the pessimistic label mitigation. As we can see here, it's just improved by 0.4. A final experiment we did is here we consider adversarial training dataset built by controlling the sampling rate of element from peak. So basically here we test against IDSs that trained on datasets that have the same size of 82 but with different number of population proportion of the population inside it. So 82, 10 represent 10% of the size of the dataset from big set, 90% of outside of this dataset, and so on. This result shows that adversarial evasion attack are significantly less effective in the majority of the IDSs when compared to IDS 82, except for IDS 75, which is normal because here we overfit the model with one type of the data. And also we notice that with sampling rate between 20 and 50%, it seems that to have very close performance in terms of reducing the danger of adversarial samples. So here in this mitigation, we get very close result to sample removal approach with AIR close to 0.6. So this is thanks to the big set here because we still have a very good performance even if we have the threat of the normal confusion sample. So furthermore, using the oversampling peak mitigation narrows the margin between the performance of the IDS trained on the mitigation like IDS 8225 and IDS 83 as the difference in AIR is almost divided by 2 here. So as a conclusion in this work, we identify the main threat that lead to extend the contradictory dataset during the adversarial training. Also, we try to insist that INA is a very critical to improve the IDS performance against adversarial attack as it allows to identify some of the quality criteria inside the dataset. In the future work, we want to investigate the applicability of the proposed approach with different strategy samplings, like try to apply this on different kind of dataset. And finally, we want to develop a data-driven approach in order to explore INA and learning this INA and try to validate, find a way or a methodology to validate these methods. Thank you. If you have a question, please don't hesitate.
Thank you very much, Hassan. I have one question. So as you're working with the GANs for quite a while now, so what was the biggest challenge getting into working with these GAN generative adversarial networks? So what was the biggest hurdle and what is the biggest challenge that you see at the moment in using GANs for cybersecurity?
Using GAN. In general, GAN has very random behavior because each time you train GAN, you have this randomness inside the discriminator and the generator, so it's not that stable when you do the training. So each time you do the attack or you do an experiment, the results are different using GAN.
Okay. So which is
because
the strength?
it's like between you have two components that attack or have a race between each other. So between the generator and the discriminator, and that's why there's this randomness.
And would you still say that it's a useful tool, and in which way is it useful to be used in production?
Yeah, of course.
In cybersecurity.
Yeah, it's very useful tool, especially when you did such things in adversarial training, because GAN can learn, let's say, when we query a system, can learn from few samples the distribution of used in a system. And so we can then augment this based on this samples that GAN has learned them. We can get the distribution and we can do an augmentation on them or using them as adversarial training. or adversarial generation.
Good. We have other questions.
I just want to add one thing because it's far now. But Hassan also did good work identifying bad practices in gun training, and especially we noticed that many things that we can find online do not keep the best model during the training process, but keep the last model of the training process. And this is very strange, honestly, but this is the practice. And if you keep the best instead of the last, you reduce a lot the variability of the performance. But it was something that Hassan identified now more than 1 year ago. So.
Good. All right. Yeah, so thanks a lot, and it's really a pleasure always seeing also your progress. Thank you very much. Then that concludes our morning.
Question?
Yes. Yeah, Marco has a question. Okay, then Marco, go ahead. No, it's fine. Yeah, it's fine.
It's a short question.
Short question.
What's the answer?
Thank you for your work, and I think it's very interesting, and I see the clear link with other subjects like digital twin, because you are able to generate a set of attacks maybe a human being never thought about. But my question is, when you generate noise, you have a slide when you explain, you have a set of a sample of data, you call it A, and you add noise to produce attacks.
It's a long way to get there.
Yes, this one. And in a digital world, it's easy. And I mean, you have a sample of data, you add noise, and you have a new sample of data. But I was wondering how you able to contextualize that sample of data to apply it to this or that context.
Okay, so this is the problem of the adversarial generation, because here we have some constraints. So if you have, and this is what's the concept of INA about. So if you have some data sets that have some features, there's some features that are identify or are functional for a type of attack, but are not functional for another type of attack. So when we want to generate a good valid sample or an impactful sample, we need to guess, or we need to know, or we need to learn these features that we can't change. So when we do the generation, we keep those features and we apply the attack generator on the other features. So and this basically just we can find this in one data set in the literature, which is in the SLKDD, but we didn't found this in the newest data set like CIS, IDS, and so on. So people try to guess these features.
Okay, so it's an open question right now, right?
Just that's ongoing work, ongoing discussion. But for instance, for CIDS 2017 and the follow-ups, they use a meta-exploit module to generate attacks. So we can go back into real world instead of data world. And instead of considering exploration of possible perturbation in data world, the idea would be to go into the real world and tune the modules, for instance, in meta-exploit to explore what could be sent and still is in attack. But more generally, we are clearly investigating this point, discussing with experts in cybersecurity in our lab. And for instance, there have been some suggestions, for instance, to try to get some insights from the snort rules that give us somehow the list of features that could be operated by an attacker freely without changing the semantic of the attack. And moreover, it could be perhaps the origin of the claim made in NSLKDD, for instance, this kind of source of information. But it's something that needs to be checked.
That's exactly what I had in my mind. Actually, how do you impact or implement it with Metasploit in order to be
Okay.
concrete?
We started a reflection on that, but there are other solutions. So that's typically the kind of thing that is in our mind now.
I have just a very
yes, Joaquin.
Very, very quick is because of the remark of Thomas before, and I think also what you were saying in link with the previous presentation that I think then we can discuss offline, Thomas. But I was thinking that something that we want to explore and that thing is interesting, I guess is the link with what you were saying, is that we would really like to see how the adversarial training is not done with AI, but with explainable AI. Like, for example, I would like to do it with Lime, in which you are model agnostic, or with SHAP, that you have kind of adding the models in order to add the explanation of what you are learning. So in our case, for example, we try to do a perfect replica of a data set, like I was saying before, and we don't want to have just a perfect replica of the data set, let's say in terms of syntax, but we would like to have a perfect replica of the data set in terms of semantics, that we are building new knowledge, because the adversary is not just doing a perfect copy of something, but is doing a perfect copy of something and then can learn and to explain things from this something that is doing the copy. So I think this is very close to what you were saying about not keeping the last model, but the best model in order to do the best learning possible. And we are curious about this, how we are going to do this kind of training with the kind of tendencies in explainable AI that could be giving much better results, maybe.
That's exactly because in future work we found that there's some studies that use SHARP to provide some approximation of ENA, but actually SHARP is just talk about important features of a class, but this is keep the semantic of the samples, or actually we need to validate this. So we need to find a way to validate this, and this is one of the future work we consider.
Yeah, I think we can do it with model agnostic or with SHAP, like you say, like you will put the game theory in place in order to add this new kind of semantics. And I think this is very interesting. So that's why I think for sure we can continue this offline, but I think we need to check this together.
And one last word, it means it's not because a feature is important that it's not functional. For instance, importer feature might be functional, but they are important for detection. And sometimes the IDS and the dataset is badly designed, and so features that could be freely changed during experimentation seems to be included in things like SHAPs and all these methods that try to explain how the decision is taken. And in this kind of context, the problem is that trying to learn ENA from this approach that just focus on how important an element participating to a decision might be a way to make a twist. And if the attacker do differently this selection, we might still end up with exactly the same problem that with BIC. That is, the attacker has a perfect way to focus only on samples for which he knows that he will perfectly evade detection. So that was a part of the reason why we didn't consider from the beginning this SHAP thing, because there is some kind of structural limitation here.
Okay. Okay, I think we can leave it here, otherwise we will not have time for lunch.
Oh, sorry.
Exactly. No, but I mean, it's so we had more discussions than I had planned in the agenda, but this is good. So therefore, I'm very thankful for everybody who participated in the discussion, and thanks again, Hassan, for the great presentation.